So pipes in series, it means that you have let us say that you have two pipes like this. The name series is obvious, they are connected one after the other. So you have let us say that the diameter of the first pipe d1, the average velocity v1, length L1, friction factor F1, and for the pipe 2 corresponding things are there. What is the, so when we consider these pipes in series and parallel, in this analysis, the analysis that we are presenting as a theoretical development, we are not considering the minor losses, we are considering only the major losses. So the head loss for the pipe 1, what is that? F1 L1 by D1 into V1 square by 2G. What is V? V is 4Q by pi D square. So in terms of the flow rate, so F1 L1 V square will be 16Q square. So 16 F1 L1 Q square, then 2G pi square D1 to the power 5, okay, where Q is the flow rate which is going through each of these pipes. So when they are in series, what is the common thing for them is the flow rate, the same flow rate is going through the two pipes. So if you have HF2, you have similar thing 16 F2 L2 Q square by 2G pi square D2 to the power 5. Now what is the concept of an equivalent pipe? That is, you replace these two pipes in series by a single pipe of some diameter, let us say D is the equivalent diameter, LE is the equivalent length, and FE is the equivalent friction factor, such that you have the same flow rate and the same head loss, okay. So it is just like an electrical circuit where you are considering the same voltage and same current flowing through that, so you find out an equivalent resistance sort of thing. So here it is like the head loss is like the pressure drop, which is like a potential drop sort of thing, and the flow rate is like a current, so to say. It is not exactly analogous mathematically, but it is just another qualitative way of looking into it. So when you have this HF as expressed as the head loss in this equivalent situation, then HF must be equal to the sum of HF1 and HF2. So if you write HF for the equivalent pipe, it is a single pipe of length LE. So from this you can write 16 FE LE, same Q is there, by 2G pi square DE to the power 5 equal to 16 F1 L1 Q square by 2G pi square D1 to the power 5 plus 16 F2 L2 Q square by 2G pi square D2 to the power 5. So from this what we can get? We can get a very important expression, that Fe Le by D to the power 5 is equal to F1 L1 by D1 to the power 5 plus F2 L2 by D2 to the power 5. So in general you have, if you have n number of such pipes in series, you have Fe Le by De to the power 5 is equal to summation of Fi Li by Di to the power 5 I equal to 1 to n. So as if it is like a equivalent resistance as the sum of the resistances, that is a simple way of looking into it. Now let us look into pipes in parallel. So when you have pipes in parallel, let us try to make a sketch of maybe a situation like this. So you have two pipes which are sort of connected in parallel, that means say they are branching off from, just let me sketch it in a bit of a different way. So let us say that you have pipes through which some fluid flow Q is coming there. Now you have two pipes with say diameters d1, length L1. So length L1 means not just straight portion plus also the curved portion, all those taken together, d1 L1 and the friction factor F1. Second pipe d2 L2, friction factor F2. So now so these pipes both are connected across these 2 points which are shown as cross. So what you can say that let us say that Q1 is the flow rate through this one, Q2 is the flow rate through this one. So you can say that Q is equal to Q1 plus Q2 if you consider the node which is given by the cross, just like Kirchhoff's current law. So the Q is distributed as Q1 and Q2. Then what about the head loss? Head losses are the same, because eventually you are talking about the difference in energy between these 2 points. No matter whether you traverse by the upper pipe or the lower pipe, eventually you end up at the same point, and the loss of energy therefore should be same as what you calculate from here or what you calculate from here. So you have HF1 is equal to HF2. So these are basic equations, and from that you can find out the equivalent length of the pipe. So you have, and for the equivalent pipe you have say HF equal to HF1 equal to HF2 and Q equal to Q1 plus Q2. So what is the HF of the equivalent pipe? 16 Fe Le Q square by 2G pi square d to the power 5, right. This is the HF of the equivalent pipe. This is equal to HF1, that is 16 F1 L1 Q1 square by 2G pi square d1 to the power 5, and this is also equal to HF2, okay. So this is HF1, this is HF2. Let us say that each is equal to some constant K. And the 16 by 2G pi square, this is a term which is like a constant for all, let us call it a C. So you can write this is Q2. So you can write Q1 is equal to, or Q1 square is equal to K into d1 to the power 5 by F1 L1 C, right. Similarly Q2 is equal to K into d2 to the power 5 by C F2 L2, and Q is K d to the power 5 by C Fe Le. Q2 square, yes, right. Since you have Q equal to Q1 plus Q2, you have from these expressions root over d to the power 5 by Fe Le is equal to root over d1 to the power 5 by F1 L1 plus root over d2 to the power 5 by f2 L2. Okay, the other terms get cancelled out. So these are expressions for the equivalent, the relationship between the equivalent and the original ones in terms of the respective diameters and the friction factors. So with this background, let us try to work out a few problems where we have the pipes connected in maybe series or parallel. So you have two pipes, two pipelines, and these two pipes, the upper one is D1 is equal to 15 centimeter and length is 150 meter. The friction factor is a constant which is 0.018. The other pipe is the diameter D2 is 12 centimeter, the length L2 is 150 meter and the friction factor is the same 0.018. It is given that Q1 is equal to Q2. You have to find out what is the loss coefficient of this valve. Okay. So the approach is very straightforward. You see, why I am illustrating this problem is the whole idea is never get tempted to use a formula which is ready-made available with you. There is a formula which is ready-made available with you and you might be tempted to use that. What should prevent you from being tempted with that is that here you have a minor loss that is not considered in this formula. Okay. So if you use that formula, it will give you erroneous solution, but obviously the concept of pipes in parallel you may use. So what are the things? You have HF1 equal to HF2, not just HF, the total head loss, so not just the friction loss. So H loss 1 is equal to H loss 2. So what is H loss 1? You have F1 L1 by D1, or we write in terms of Q, 16 F1 L1 Q1 square by 2G pi square D1 to the power 5 plus the K valve into V square by 2G. So V1 square by 2G is as good as V1 is 4Q by pi D square. So 16 Q1 square by pi square D1 to the power 4 2G, that is V1 square by 2G, is equal to the head loss at 2, that is 16 F2L2 by 2G pi square D2 to the power 5 into Q2 square, right, and it is given that Q1 equal to Q2 given. So you can cancel that from the two sides and get the value of the K valve straight away, a very simple exercise. The answer is K valve is 18.62. Okay. Next we work out another problem. you have two pipes of length L and diameters D1 and D2, and they are arranged in parallel. When they are arranged in parallel, the loss of head for a particular flow rate Q is the flow rate, the loss of head is H1, and the same pipes when they are arranged in series, the loss of head is H2. It is given as D1 by D2 is equal to 2. Find H1 by H2, neglect the minor losses and assume a constant friction coefficient to be the same for all the pipes. So, the two important assumptions, that minor losses are neglected, and number 2, friction coefficient or the friction factor is a constant, and that constant value is same for all the pipes. Okay. Under which conditions friction factor you have a constant virtually? For very high Reynolds number, highly turbulent flow, it will become only a function of epsilon by d. So, but here the diameters are changing, so we are assuming that epsilon is also different for the two pipes such that epsilon by d remains the same, so that the friction factor remains the same. So, when the two pipes are connected in series, so you can work this out through the equivalent resistance concept. So, when they are in series, you have what is the condition for the equivalent Fe Le by d to the power 5 is equal to F1 L1 by d1 to the power 5 plus F2 L2 by d2 to the power 5. This is for the series. And now the equivalent thing, see, equivalent thing has combinations of 3 parameters, and see, it is not important what are the individual values of these parameters, it is important that you collectively choose them to satisfy this constraint, that should be good enough. That means you may choose your equivalent friction factor or equivalent length in such a way that you will get some equivalent diameter, or you may choose equivalent friction factor and equivalent diameter as to be something so as to get some equivalent length. So, you may take any of these out of 3 2 very freely, and the third one you get from this expression. Let us say that we assume that the two pipes are of the same length, right. So, let us consider that Le, or in fact if you see that it is Fe Le by d to the power 5, that is going to be solely important for the head loss. So, even if you do not assume any particular value, that will not matter. So, if you consider the head loss, what is that? 16 Fe Le q square by 2g pi square d to the power 5, right. So, in place of so you can clearly see that you get an expression where you have Fe Le by d to the power of 5. So, let us say that you write in place of that 16 q square by 2g pi square, then you write F1 L1 by d1 to the power 5 plus F2 L2 by d2 to the power 5. This is given as H2, this is series. If they are in parallel, again HF formula is the same, but expression for so this you have 16 q square by 2g pi square, then you have 1 by d to the power 5 by Fe Le. right, and that you can substitute in place of this one. Right, that is d to the power 5 by FELE, and this is given as H2, sorry, this is given as H1. Just you divide by these two and you will get a ratio. When you divide, you will get a ratio of d1 by d2, and L1 and L2 are the same. So that ratio will give a number. So this, when you divide, you will just get a number. F1 and F2 are the same, so those effects will cancel and it will be expressed solely in the as a function of d1 by d2 if you write H1 by H2. So the H1 by H2, the answer is 0.02188, that is the answer. Let us work out maybe another problem. The problem statement is like this, that initially, so you can see that here there are pipes A, D, B, D and DC. So this is just shown by schematic, so not the width is width being shown. So here initially only the part AC was there was no branch BD, and then the flow rate was 100 liter per second, that is given. So Q0 is 100 liter per second and the length of AC is 1000 meter, that is 1 kilometer. To increase the flow rate, another pipe BD is added. Okay. Estimate the length of the new pipe, that is the problem. All diameters are equal, so all diameters are equal and assume the same length for all the pipes, not for all the pipes, that is L1 equal to L2, that is same length for the two parallel pipes, and same friction factor for all pipes. So friction factors are also equal. Okay, and it is given that there is a 30% enhancement in the flow rate because of this. So you have to find out basically L1 and L2, that is the question. So let us say that there is a flow rate Q1 through L1 and Q2 through L2, and the total Q is sum of Q1 and Q2. So then you can write, so the head losses, if you neglect this elevation difference, the head losses should be what? The head loss for AD and head loss for BD, they should be the same, they are like pipes in parallel. So if their head losses are same, head loss is function of Q, F and L. So you have F and L are same, therefore Q should be same. So HF AD equal to HF BD, that will give you Q1 equal to Q2, and therefore you have Q3 which is either equal to 2Q1 or 2Q2. all the same. Then what is the total head loss? That is capital H. So, we will not write the modified equation in all details, you have just seen that this capital H should be compensating the total head loss. So, the head loss in AD plus the head loss in DC, right. So, this will be a function of Q3, because head loss in AD is a function of Q1, Q1 may be expressed as a function of Q3 and head loss in DC is a function of Q3, and the head loss when this branch system was not there, still the head loss would be the same, right. So, when BD is not there, then the head loss is the head loss for the length AC with the original flow rate as Q0. So, 16 F L is L1 plus L3 into Q0 square by 2G pi square into d to the power 5, and it is given as that there is a 30% enhancement in Q, that means Q3 by Q0 is 1.3. So, from that you can find out the missing length. You have to keep in mind that total L1 plus L3 is 1000 meter. So, just assume these as some x and this is 1000 minus x and this is also then x. You can solve for that, remaining things are given. Let us maybe look into another problem very briefly. So, let us say that you have two pipes or a pipeline, it has a diameter say d0 and the velocity v0, it is having some length say L0. To increase the flow rate, a new arrangement is made. What is the new arrangement? The new arrangement is a branch is taken away from the midpoint of this one. So, this is L0, this is L0 by 2 and this is L0 by 2. So, the diameter is the same, the diameter is d0 for the second arrangement as well. You have to find the change in flow rate, say here flow rate is Q0, here the flow rate is Q1. So, you have to find out what is Q1 by Q0 given HF1 is equal to or HF0 is equal to HF1. Okay. So, this is a straightforward pipe series parallel problem. So, only thing is what you do, you replace this by an equivalent pipe. So, if you replace this by an equivalent pipe, these are two pipes in parallel. So, root over d to the power 5 by FELE is equal to root over d1 to the power 5 by F1 L1 plus root over d2 to the power 5 by F2 L2. Here all F's are the same. Let us consider that the equivalent friction coefficient also the same. L1 is what? L0 by 2, L2 is L0 by 2, D1 and D2 are the same, which is equal to D, same diameter pipe. So, this is D to the power 5, this is D to the power 5. So, let us say that the equivalent diameter is also D. So, you can find out an equivalent length in terms of as a function of L0, right. So, then this entire pipe as if is replaced by a pipe of length L0 plus L equivalent, and you have HF1 is equal to 16 F L0 plus L equivalent so by into Q square by 2G pi square d to the power 5 and HF0 is 16F, oh sorry, this is L0 by 2, L0 by 2 plus L equivalent. Sorry, this is L0 by 2, just correct it, this is L0 by 2, half half. So 16F L0 Q0 square by 2G pi square d to the power 5. From here, since these two are equal, you can find out what is Q1 by Q0. The answer is that the increment is 26.48%. Okay. So this is just very simple equivalent pipe system analysis. So let us stop here today for this lecture, and we will continue with the next lecture with a new topic. Thank you.